In the last section, we were comparing two populations by finding the mean for one group and then finding the mean for the other group and then subtracting those two means. So in the last section, we were finding the difference of means. This was the last lesson. Okay, in this section, we're going to deal with paired data. So instead of finding the mean for one group and then finding the mean of the other group and then finding the difference, we're going to have paired data. So we're going to find all the differences and then take the mean of all those differences. So the difference is we're going to find the mean of all of the differences. So we're going to do this with paired data. Data are paired when the observations are collected in pairs, or the observations in one group are naturally related to observations in the other group. Some common ways that this occurs are with married couples, before and after, and with twins. Okay. Now, are these the only ways to get paired data? No. There's a problem in the book where they do some kind of measurement on the left arm and they compare it to the right arm for the same people. That's paired data. So if you know that the data are paired, you can and must take advantage of it. There is no test to determine whether the data are paired. You just have to think about it logically. Once we know data are paired, we can examine the pairwise differences. So because it is only the differences we care about, the differences becomes our data, and we ignore the two original sets of data. So because there's only one set of data, we're going to return to a one-sample t-test. A paired t-test is just a one-sample t-test for the mean of the pairwise differences. The sample size is the number of pairs. So like the other hypothesis tests that we've done, you're going to start with the hypotheses. So HO is going to be that mu for the differences is going to equal some hypothesized value. This will usually be 0. 3 options for the alternative hypothesis. Mu for these differences could be greater than the hypothesized value. It could be less than the hypothesized value, or it could be just not equal to. Okay, like in the last section, the p-value is either going to be the area right of t or the area left of t, or for a two-tailed test it is double, and then you have your choice. You could go the area right of t, or double the area left of t. Alright, the conditions are mostly the same. You have your random or representative condition, but remember to put this in context. Your second condition, there's two ways to satisfy it, either with the CLT or if the population is approximately normally distributed. So either with the CLT, which means number of pairs, so not the total number, the number of pairs has to be at least 30, okay, or distribution of differences is approximately normal. So in the last section, the third condition was that the samples were independent of each other, and now it's the opposite. The third condition is that the samples are paired. The formula for t is the same format that we're used to. So in the numerator, you have actual minus predicted, where actual is the x bar of all the differences, and then the predicted is the hypothesized value. Then we divide by the standard deviation of the differences divided by radical n. So for examples 1 and 2, we're just reading the problem and figuring out, is it paired or not? An engineering association wants to see if there is a difference in the mean annual salary for electrical engineers and chemical engineers. A random sample of electrical engineers is surveyed about their annual income. Another random sample of chemical engineers is surveyed about their annual income. Is this an example of paired samples? Well, no, it's not. It looks like we just have two independent samples. They're not telling us that the engineers are brothers and sisters, or that they're taking one from each company. So they are independent, so that is not a paired sample. And number 2, a pharmaceutical company wants to test its new weight loss drug. Before giving the drug to volunteers, company researchers weigh each person. After a month of using the drug, each person's weight is measured again. So this is paired because it's the same person being weighed before and after using the weight loss drug. And now on number 3, we're going to carry out an entire hypothesis test. Can playing chess improve your memory? In the study, students who had not previously played chess participated in a program in which they took chess lessons and played chess daily for 9 months. Each student took a memory test before starting the chess program and again at the end of the 9-month period. Carry out a hypothesis test to determine if there is evidence that playing chess improves memory. So we're going to start with hypotheses. Our null hypothesis is going to be that the average difference is 0. And then our our alternative. Alright, so the keyword here is we're trying to see if memory improved. So I'm going to write that it's greater than 0. Now, it's not necessarily wrong if you write less than 0. What you have to do is indicate which way you are finding the difference. So I'm going to write that the difference that I used is post minus pre. And so if I want memory to improve, then post minus pre needs to be positive. If you subtract the other way, if you do pre minus post, then you want the difference to be negative. Okay, after the hypotheses, and after we indicate which way we did the subtraction, we have to check the conditions. So the first condition is random or representative. So they don't mention anything about that, so we will assume. Okay, and then the second condition is either the CLT. CLT doesn't work here because we only have 12 students. So we're going to have to use the plots. So now would be a good time to pause the video and put all the data into your calculator. So put the data for pre-test in L1 and the post-test data in L2. So go ahead and resume the video once you've entered in that data. Okay, so now that the data is in L1 and L2, remember that for a paired t-test, you don't even use the original data. The data you care about is the difference between the two lists. So in L3, go to the top of L3, so make sure your cursor is on L3 and not underneath it. So in L3, type, and so the way I did my subtraction, you need to do L2 minus L1. So on L3, type L2 minus L1. The way you type L2 is second 2, and the way you type L1 is second 1. So on L3, type L2 minus L1 and hit enter. So then all the differences should now be in L3. And now we're going to check the second condition by checking either a box plot, a histogram, or a normal probability plot. So I'm going to do a normal probability plot, and what a surprise, it looks good. I see a roughly diagonal straight line. So a normal probability plot of the differences displays a roughly diagonal straight line indicating the population is approximately normal. Okay, I'm going to continue on the next page. Condition 3 is that the data are paired. Okay, once you've satisfied the conditions, you need to say what kind of test you're going to do and what model you're going to use. So since the conditions are met, we will use a student's t-model. And remember, the degrees of freedom are the number of pairs minus 1. So there were 12 students, and so our degrees of freedom is 11. And the test we're going to do is a paired t-test. So to conduct Okay, on your calculator, it's not actually called a paired t-test. It's just a regular t-test that you do on the differences. So go to Stat, Test, and it's number 2, t-test. Okay, we had data. Our mu from our null hypothesis was 0. The list should be in L3. Frequency list we didn't use, so choose 1. And then we want the greater than option, and we're going to calculate. Okay, so I'm going to show my work to help you guys with a multiple choice question that you might see. So the formula is actual minus predicted. So they tell us the actual average difference, and you'll get this from the calculator after you run the test, is 144.58. The hypothesized difference was 0. And we're going to divide that by the standard deviation of the differences. Divided by radical n, so radical 12. So that equals 4.564. We also need to provide the p-value. So the p-value is 4.057 times 10 to the negative 4th. So that's highly unlikely. So under the assumption that the average difference in memory score is 0, the odds that we would get a sample like ours, if we took a sample of 12, the odds that we would find an average difference of 144.58 or higher, the odds of that are really small, close to 0. So now we need to make the conclusion of our test. So whenever the p-value is small, we reject the null hypothesis, or HO. And whenever you reject, you do have evidence. Alright, so your last sentence always needs to talk about HA in context. HA was that mu D was greater than 0, which means memory improved. So we have convincing evidence that playing chess improves memory.